This is lesson 4.4, analyzing quadratic functions of the form y equals a multiplied by x minus p all squared plus q. Now each constant, a, p, and q in that equation changes certain aspects of the graph of the quadratic equation. So even though when we first look at this equation it doesn't quite look like a quadratic, but it is. It's just a quadratic in standard form. So we're going to look at how a, p, and q affect the way the graph of these quadratic equations look. Each one will affect it in a different way. So let's first look at the effect of changing q in y equals x squared plus q. So we're going to graph each of the following quadratic equations and then talk about our results. First of all, this first equation here, y equals x squared, this is our most generic quadratic equation. It's kind of like the original quadratic. So I'm going to go ahead and graph it. I'll use a table of values to graph it this first time, but after that we're going to try and memorize it because we're going to use it a lot. It's a good template for the rest of our quadratic equations. So looking at it, we got a table of values here. And for x, I'm going to use values from like -3 to +3. So I got all these. And plugging those in, I'm going to get values for y that are 9, 4, 1, 0, 1, 4, 9. I'm going to graph each of these quadratics in different colors as well. So my first graph, our original, I'll do in a dark color, say red for that. So let's graph our points. We got a point at -3 and 9, which is about right here. And then we have one at -2 and 4, right here. -1 and 1, 0, 0, 1, 1, 2, 4, and 3, 9. So there we go. Those are all our points. Now connecting them to get our shape here. There we go. That is our original quadratic function. So I just want you to notice the pattern here for our quadratic. We have, it starts at its vertex here at 0, 0, and then the next points are always over 1, up 1. The next point after that is over 1, up 3. And the next point after that is just yet again over 1, but up 5. So that'll be our pattern for our original quadratic equation. Now, when we change, for example, right now, the value of q, it's going to give us a new function. So let's see what it would look like. For our next graph, I'll use this purple. Now, what would happen to our x values here if we added 4 like in our second function? Well, instead of having 9, it would be 13. And instead of 4, it would be 8. So our y values are increasing by a value of 4 each time. So the shape shouldn't change, it's just changing the location of our quadratic, and it's increasing it by 4. So our vertex, instead of at 0, 0, will now be at 0, 4. And then each point after that will continue the pattern that we had of over 1, up 2, over 1, up 3, except it's all increasing by 4 in its height. So we got over 1, up 1, both sides, and then over 1, up 4, on both sides, and so on. Since our graph doesn't quite reach the next point, I'm just going to keep it there, and then we're going to get our parabola for that one. So it has the same shape, just it's shifted up 4. So let's make a note of that. It shifts up. What about our last quadratic function here? Let's do a dark purple for that one. Y equals x squared minus 4. Well, here, if you take a wild guess, it's not going to change the shape. It's yet again going to shift in a direction but now it's shifting downwards. So we're going to get our quadratic starting 4 lower than the original. So we got a vertex of 0, -4 now. Right about there. And following our pattern, over 1, up 1. Over 1, up 3. Over 1, up 5. 1, 2, 3, 4, 5. Right around there. And we could do another one of over 1, up 7. We got 1, 2, 3, 4. About up here and up here. So our last quadratic function looks like that. So the shape never changes, but it's shifting either upwards or downwards when we change the value of q. So looking at our notes here, we're going to say, when q is positive, the graph moves upwards. And when q is negative, the graph moves downwards. So those are the rules for changing value of q. What about our next variable here? What happens when we change the value of p now in the equation? So yet again, we need to graph our original here, and I'll do it in red. And we start at vertex 0, 0, over 1, up 1, starting at the vertex over 2, up 4, both sides, and then over 3, up 9. Way up here. So there's our original quadratic function of y equals x squared. Well, what about when we look at y equals x plus 3 all squared? Let's try it out with a table of values, for example, in this case. So we got x and y. Let's plug in some values. So when we have our original ones that we used, what's going to happen this time? Well, -3 plus 3 is just 0, so 0 squared is 0. -2 plus 3 is positive 1, so that's just going to give you 1. -1 plus 3 is positive 2, so that'll give you 4. And 0 plus 3 is 3. 3 squared is 9. And if we continued on, we'd probably get greater and greater numbers. Well, let's look at what the graph is showing us so far. We have -3 and 0 right there. -2 and 1 right around there. -1 and 4 right around there. And 0 and 9. Looking at that, that kind of looks like half of the parabola that we want. So if we go ahead and match all the other sides here, we would get our parabola. So what happened to our original parabola here? Well, the shape didn't change again. Instead, it shifted. But instead of shifting up and down, it shifted to the left. So the effects of changing our p-values is going to now shift our graph either left or right. And since we determined that when it's positive, it's shifting left, now we can say that when it's negative, it's probably going to shift right. So our other graph here should be 3 in the other direction from our original graph here. So we're going to have it starting there and filling in our points as so. We'll get our graph like this. There are our 3 quadratic functions there. All the same, just shifted in different directions. Hence, in our notes here, we can say when p is negative, the graph moves right. And when p is positive, the graph moves left. So remember that when it's positive, it's actually going to shift in the negative direction, and when it's negative, it'll shift in the positive direction. So it'll be the opposite in this case, where it was stayed the same in our Q case. Well, what's our last variable here that we need to look at? The effect of changing a in y equals ax squared. So for these quadratic functions, it'll be different from our first two. It's not going to shift anywhere. It's actually going to affect the shape here. So let's start off with our original again. Remember, have it in red. Starting at a vertex of 0, 0, over 1, up 1, over 1, up 1, over 2, up 4, over 3, up 9. Filling that in. Perfect. What about y equals 2x squared? Let's see. What is going to affect the graph there? Well, our vertex of 0, 0 will still be 0, 0. So we're still going to start at our original point there. What about our point of 1? Well, if we plug in 1 for x, we're going to get 1 squared is 1 times 2. So now it's actually going to double in height. So it'll be more around here. If we plug in 2 now, we get 2 squared is 4. 4 times 2 is now 8. So our point will be here on either side. So our quadratic now looks a little skinnier, no? So in this case, when we multiply by a factor of 2, it stretched horizontally. While y equals negative 2x squared should look the same, the only difference here is that our negative value here is going to flip the graph. Because when we have a negative leading coefficient, it's going to be a sad face. So our graph will be skinnier, stretched totally like our second graph there, except facing downwards. So we get a graph like so. What about y equals 1/2 squared? What's going to happen when we have that? Let's use green. Well, plugging in for 0 again, we're still going to always start at our original point here of 0, 0, our vertex. Well, plugging in 1 there, 1 squared is 1 times 1/2 is just 1/2. So it'll be in between 0 and 1 here, points like that. Well, plugging in 2 now, 2 squared is 4 times 1/2 is just 2. So our next point is going to be at a height of 2. Well, let's do another point. How about 3? 3 squared is 9, and 9 divided by 2 is about 4.5. So we're going to have points around there. So our graph is going to start looking a little like so. Well, instead of getting stretched horizontally, it now looks like it's getting smushed. Hence we call that compressed graphs. So our next graph here of y equals negative 1/2 x squared will be very similar to our graph we just made, except because of the negative then, again, it is flipped and compressed. So, should look like so. Start at our original, our vertex of 0, 0, and we're compressing in the negative direction. So, first point's at negative 1/2, and then at 2, and then negative 4.5, right around there. And there we go. Here's our next parabola there, our compressed negative parabola. So we have a bit of a trend here. From our original graph, when we have negative leading coefficients, it's going to be flipped and be a opening downwards parabola, and then depending on what value it's being multiplied, it's either going to be stretched or compressed.